So now we're applying this concept to the estimation of the spatial lag model. And again, we will start by the likelihood function. Then once we have it, we know what to do. First order conditions, the partials, the scores, we solve them. It's an optimization problem. Then we have our estimates, and then we have to get some sense of the precision of this estimation. So then we go to the asymptotic variance matrix, which is a monster. It's a very non-standard result. And you don't see this anywhere in time series. And then we have to say something about model fit because the usual R-square does not apply. So the likelihood function, we know our reduced form. Remember, I stressed this is not a conditional model. This is a simultaneous model, which means it's a model for the full pattern of your dependent variable. So it's not my house price is determined by my neighbor's house price, but let's determine the full spatial pattern of all the house prices in the whole city. That's this left-hand side. And we determine it as a result of the reduced form, which only has exogenous variables, as we call them, and error terms. Whereas the randomness is here in the error term. There's no randomness in the X, or if there is, we can ignore it, as we said. The randomness of Y comes only from the randomness of the error term. So this is the driver. Now, because of this inverse term here, if we compute the spatially lagged dependent variable, we just put a W in front of here. That puts a W in front of here, and then a W in front of here. As a result, because the error term is in here and it doesn't disappear, we have the problem of the endogeneity. So we talked about that a little bit when we went over the different data generating processes. So spatially lagged dependent variable is correlated with the error term. We don't want that. That's endogeneity. We talked about using instruments and instrumental variables to fix that. We'll do that on Wednesday. Here, we go the other route and we model everything, which means we assume a distribution for the error term. From that, we figure out the error term we can't see, but we can see the Y. So from the distribution for the error term, we get the distribution for the dependent variable, the Y, which we can see. And then we get that expression, we maximize it for the parameters, and we're in business, right? The error term, in general, can be multivariate normal. So this is the very general case. I'm going to simplify that very quickly and just go back to our sigma squared I case. Sigma squared I means constant variance, no correlation, right? This sigma means we could have all kinds of other stuff as well. Right? We're not going to go there. So the point of departure is a multivariate normal distribution for the error term. Right? Classic statistics, you guys who've taken math stat know how to do this. The distribution of a multivariate normal random variable, the log likelihood has essentially this major part, which is a weighted sum of squares, sum of squares of the error term. This is the log of a determinant of your full variance covariance matrix. And this is just 2 pi, One thing that if you use software that isn't always clear when they report the log likelihood, the result, is whether or not they include this 2 pi thing. Since it's constant, it doesn't matter. The maximum is going to be the same. But some do report it, others don't. So then, you know, people come to me and say, oh, I run this and so, and I get a different number with the same parameters. Well, if you do the calculation, it's exactly this 2π term. In our simplified case, this is the log of sigma squared times the identity matrix, the determinant of that. So we move sigma squared out. The determinant of identity matrix is 1, so we don't have to worry about it. And same here, the sigma squared I inverted, we don't have to worry about the identity part, but we divide by sigma squared. So if we have our classic result, this would be E prime E divided by sigma squared, right? Instead of this big inverse thing. So maximizing the log likelihood function for the classic problem of finding the mean and the variance matrix for normally multivariate normal random variables is essentially finding the minimum of this, because it's maximum of a negative, which is the minimum, which is weighted least squares. Okay.
Why do we care about the middle term? Whatever
This one?
determinant of the.
We care about it. It's a scalar. It scales the whole thing. But for the optimization, it doesn't matter, because it scales everything the same way. So as long as you have that, if you have your maximum, of course, the number is not going to be the same, but the parameter values will be the same. That's what matters. Okay, so this is where it gets tricky. Okay. The assumption of multivariate normality is for the error terms. We don't see the error terms. They're just a figment of our imagination. It's mathematical concept, right? We do see Y. Now, because the error terms have a distribution, Y will have a distribution. What is that distribution? Well, one thing we already know, because it's a linear transformation, it's a linear function, linearity keeps the normality. So that's good. We know it's going to be normal, but there is something, and I mentioned this before, you know, when you have a transformation of a random variable, the distribution of the function is not that necessarily the function of the distribution. Okay. Again, this is classic homework stuff. You know, you have a variable that is distributed as Poisson with a given mean. What is the distribution of the square of that random variable? And then you have to figure that out. And to figure it out, there is a concept is called a Jacobian. The Jacobian of the transformation. And it sounds very complicated, and it looks very complicated, but it isn't. It's just a scaling factor. It's a scalar. It's something like 0.5 or 0.7 or 2 that makes sure that the area under the distribution, which should sum to 1, you know, all the probabilities sum to 1 in continuous variables, that means that the integral sums to 1. That means that the area under the function is 1. So this Jacobian makes sure that the area under the distribution for your function of your random variable sums to 1. So it takes the original one, and you can, again, you can play with this and graph this, and you'll see it won't sum to 1. So then you need something to rescale that to make it a proper distribution, to make sure, in other words, that all the probabilities sum to 1, not more than 1, not less than 1, right? So you just rescale everything. That's the Jacobian. It's the monster because it's a partial derivative again, right? So if we have, and depending on the textbook that you use, they use inverses or not, but essentially you write the error term. This one has a random part. This is what it's equal to. It has Y through this identity one. It has the spatially lagged of spatial lag of y with rho, and it has x and beta, right? Given the distribution for E, what is the distribution for Y, taking into account the fact that they're functionally related. And that is where the Jacobian comes in. The Jacobian is the determinant of the partial derivative of the function with respect to Y. This looks very complicated. In the spatial lag model, it's the partial derivative of this with respect to Y, which is the determinant of that matrix. The determinant of this matrix is the scaling factor. So a determinant of the matrix is not a matrix, it's just a number. Okay. So this is a number that scales the distribution so that it's proper. Right? The problem with this is that this is a determinant of a big matrix. Even though the determinant itself is a single number, this matrix is n by n. If you have 10,000 observations, it's a 10,000 by 10,000 matrix. That's big. Right? And computing determinants of big matrices becomes a numerical problem. You get rounding errors and stuff like that. So at some point, it doesn't work anymore. Then you're in trouble. So the Jacobian enters the log likelihood. Why have you never seen this if you never had done spatial analysis? Because in regular likelihood, it doesn't matter. In regular likelihood, this partial derivative is 1, so it's not an issue. So it's a 1-for-1. Linear regression, 1-for-1. Spatial lag model, no longer 1-for-1. You need this rescaling thing. As a result, the log likelihood becomes this nice little expression here in yellow. So to keep it simple, as I said, I'm going to make no assumptions about heteroscedasticity or anything like that. We no longer have independence, so we can't just do the product of the individual likelihoods or the sum of the individual log likelihoods. We have to do the whole thing in one shot. So we write the log likelihood of the full sample. This whole vector of y, the full y, becomes a matrix expression. This last part is very familiar. This is essentially least squares. All right, these are the residuals. They become residuals as functions of rho and beta, divided by this sigma square times 2. And since it's maximizing the negative of this, that's the same as minimizing least squares. But that doesn't get us the right estimate because of this other term here, which messes everything up. If this other term were a constant, we wouldn't have to worry about it. It would be the same thing as the pi thing. You know, it just moves everything up or down, doesn't change the maximum. But it's not a constant, it's a function of rho. So depending on what rho is, the scaling factor will be something different. In other words, if you do some kind of optimization, for every value of rho, you will have to recalculate this determinant. Recalculate the n by n determinant. Okay. How do we solve this problem? Always the same thing. Numerical optimization, we get the first partial derivatives and go to work. As it turns out, I'm going to go over this very quickly. You can read this at your leisure. There's some simplifying results that allow us to express the estimates for beta and for sigma square as functions of rho, so that we end up with what is called a concentrated likelihood function or concentrated log likelihood function, which is only a function of rho and these residuals, which you can compute ahead of time. So here, if you look at this, we can run 2 extra regressions. You get 2 estimates of beta, they don't change. The true estimate of your betas is the difference between B0 and BL differentiated by rho. So the true parameter is a function of rho, but these two parts, they're not functions of rho. So you just compute them, and then you substitute the whole thing in the likelihood. Same about the residuals. You can compute them ahead of time, and they're a function of rho, the real ones. So then you plug this in, and the whole business is a function of rho only, which means nonlinear optimization over a single parameter piece of cake. It's very easy to do. It's no longer a vector of partial derivatives or any of that stuff. It's just one. You know, there are very efficient methods to do this, bisection search and things like that, golden rule search. You basically, you know what the parameter space is. This is, I didn't talk about this, but in logs don't work for negative numbers. They have to be positive. That puts a constraint. Remember, I have to do log of the determinant that has rho in it. That puts a constraint on the parameter space, the values that rho can take, to assure that we don't get negative numbers there. And that's determined by the largest and the smallest eigenvalue of the weights matrix. So we're back to our weights matrix. If we have rho standardized weights, the largest eigenvalue is 1. The smallest one is a little more negative than -1. Most people ignore that. So they go -2 plus. That's not actually correct, but it's good enough. Because you don't actually want to have a parameter that's negative and larger than 1 in absolute value, which again runs counter to Tobler's law, because it means things get more important as they're further away. That's not right. So because we have these bounds, we could just start in the middle and see what our likelihood is, or log likelihood is. And then we cut the two halves in half and evaluate the likelihood in both parts. And then we see in which direction we go up and in which direction we go down. And then we go to the part where we go up. And then we do it again. We cut it in half. That's called bisection search because it's always half. And after a finite number of steps, I think 6 or 7, you have a very high degree of precision and you're done. There's also a slightly more efficient way to do this, which is golden search, where it's not exactly the midpoint, but there's a little bit off. And in practice, it doesn't make any difference in this case. So we're in business. We got our parameters. Then we need to know something about the precision of those parameters. And that's where it gets complicated. That's where we get to our friend, the information matrix, which requires these partial derivatives and then evaluating their expected value. You want to see how that works, you can look at my dissertation. It's very complicated. It requires, let me put it this way, a love for matrix calculus, okay, which is not given to everybody. But, you know, you get the result, and then the asymptotic variance matrix is the inverse of the information matrix. Now, the good news is that we can see what this information matrix looks like. The bad news is because the asymptotic variance matrix is the inverse, we don't know what that looks like. Okay. So, for your amusement, this is the form of the asymptotic variance matrix. With, I don't know how familiar you are with this, but this is x prime x. Remember, this is before the inverse, right? In the least squares case, remember sigma square x prime x inverse, that's the inverse of this part, okay? So that's the classic least squares case. This pertains to the beta coefficients. This pertains to sigma squared. Between sigma square and the beta coefficients, we have zeros. So the inverse of this box here will also be block diagonal. In other words, signal and noise, remember, the precision of the error term has nothing to do with the precision of your beta estimates. However, this is lost here. So in particular, the precision of the rho parameter, your spatial autoregressive parameter, will affect the precision of your beta estimates. That is non-standard behavior, okay? The first time a traditionally trained statistician or econometrician sees this, they think they made a mistake. No, it's not a mistake. It's a non-standard property, and it has to do with the reduced form, which ties all this stuff together actually in a non-linear way. And that gets translated in this. So there's a lot of traces in here. You see these kind of monsters, inverses of n by n matrices. You compute all the pieces, you plug them in here, then you take the inverse of that. Okay. So computationally, very heavy. Sometimes some of the earlier estimators software wouldn't compute this, but they would do a likelihood ratio test because that's easy. You do the maximization, you get your likelihood function for the spatial model. The constrained model is least squares. If you assume normality, you can compute the likelihood for that, and then you can do a likelihood ratio test, which would test the significance of rho, and for the betas, you don't have to worry about it. Okay. Inverse of the information matrix, not block diagonal, no analytical expression, all bad news, all bad news all around, okay? This day and age, less so, because we have developed some procedures to shortcuts, basically. And the most important of which is the power expansion. When you do the inverse of I minus rho W, you can approximate that by a power expansion of I plus rho W plus rho square W square, and so on. Same thing we saw in the reduced form of the lag model. Okay, residuals and model fit. What is the predicted value? And here we have, again, to remember that this is a simultaneous model. So the only thing that is a full validity is the reduced form. If you look at the predicted value in this expression, what is here on the right-hand side is the spatial lag of y, but you don't know what y is. You're trying to predict y. So why would you use observed y at the neighbors to predict y at a given location? In my book, that's called cheating. So that's a conditional perspective where you assume more information than you actually have because you don't know what these y values at the neighbors are. You're trying to predict them. Remember, I am my neighbor's neighbor. So I use my neighbors to predict me. The neighbors use me to predict them. You can't have it both ways. Right? What you can have is the same, our friend, the reduced form, which unfortunately, again, requires this inverse matrix. Luckily, the power approximation is pretty good, especially when, and you can do it yourself, when rho is not very large, you don't need to go very high to get negligible values. So do rho 0.2, put it to the 10th power, that's already a very small number, right? So you get decent approximations without having to go crazy in these power approximations. And as it turns out, there's a very easy way to compute the lag of X and then the lag of X. So computationally, that's not that bad. Residuals, same problem. Do we assume that we know what WY is, or do we not? So the first case, what I call naive residuals, these are actually the ones used in specification tests. the LM test that we were talking about. Prediction error, again, uses the reduced form. Prediction error will give you a more realistic perspective of how well your model does. The one that assumes the neighbors being observed is cheating, right?
Could you go back to the previous slide?
This one?
Yeah. How do we make sure that the inverse matrix always exists?
Okay, good question. So how do we make sure the inverse exists? The key here is the parameter space. Because of the range that we allow rho to be in, and if the weights are rho standardized, we can actually show that the inverse always exists. But this is actually if you go to the formal proofs, this is a condition. The inverse has to exist. And it exists under those conditions.
So the W times the product WY actually is the weighting matrix.
This one.
Yeah.
Yeah.
What is the rho again? Sorry, what is the interpretation of the rho?
Rho is the parameter that scales this in the regression. So we go back to the full regression. I don't think I have it here. Yeah.
Yeah, so the Y, they're the same Ys, like.
They're the same Ys, yeah.
Okay, it's my neighbor, the influence neighbor only.
It's the average of the neighbor, so if these are house prices, this is the average of my neighbor's house prices. How important is that in terms of driving my house price? But that's a structural form. Really, it's not the neighbor's price that matters, but it's the neighbor's house characteristics which come out of this reduced form.
This, and so we have to, in order to ensure this inverse matrix exists, so it depends on how we construct the neighbor.
Okay, yes and no. So the inverse will always exist if the weights are rho standardized, so that not this, it's very confusing. ROW standardized, not RHO standardized, okay? RHO is the parameter. ROW is the row in the matrix. So it's rho standardized in the matrix. And if your parameter estimate for the RHO is in the proper parameter space, that guarantees that the inverse exists. Now, if your weights are not ROW standardized, then your parameter space will have to be adjusted. If you violate that, and we'll see later when we run instrumental variables, it's not guaranteed that RHO is less than 1. And sometimes you get values larger than 1, and then the inverse does not exist. Okay. So R square doesn't count. We can do some pseudo R square, which is a squared correlation between observed and predicted. And then again, we're in the same problem. What kind of predicted do we use? It's not the classic interpretation of explained variance, but it is something we can use as a rough guide to compare how well models do. We can also use the maximized log likelihood. As I mentioned before, that's not a measure of fit, even though it looks like a measure of fit. It's just a probability, a joint probability. And as long as we have the same dependent variable, because it's the same joint distribution, these are comparable. Largest value is the best, because in this case, it's going to be the least negative will be the largest. And as we've already seen in the context of OLS, we have information criteria, which are kind of like an adjusted R squares in that they correct for the number of explanatory variables. And we've already seen in the lab notes, the AIC and then the BIC or Schwarz criterion, where small is better. The values don't really matter that much, it's the relative comparison that